Hello, AP Physics. It's your teacher, Steven Zawicki. Today we're going to be learning about friction and about some of those intricacies that we did not touch on in regular physics. So the first thing that we need to know is that there are two kinds of friction. The first kind is static, and the second kind is called kinetic. So just from the names, we should be able to understand kind of what they mean. So static friction is friction acting on an object that is not moving. Kinetic friction is friction that is acting on an object that it is moving, right? Static, right? We could talk about static electricity. These are electrons that are stuck. Kinetic, right? We just finished kinematics. That is the study of motion. So this will be friction of an object in motion. So let's say that we start pushing on a box, and this box is on the ground, right? And we start applying some force to the right. So this will be the force of a push. Friction is going to be resisting that motion. So we just talked about passive versus um, active forces, and friction is always going to be a passive force. It always is going to react due to another force acting on the object. So at the moment, our force of friction in our picture causes our two forces to be equal, which means that there's no acceleration, right? There's the object that was stationary, we're pushing on it, but the force of friction is resisting it. So this is what's called static friction. Now we can redraw this so that there are our friction force is actually smaller than it was before. Let's say our force of static friction uh, can't handle it, so then we get force of friction, and now there is some sort of net acceleration, right? So if I was to draw the acceleration, right, it would be the difference. So there is some sort of acceleration to the right, okay? Now, static friction can be called what is broken, and then we get kinetic friction. If we were to look at a graph of force and time, we would see that the force sensor increases until we hit our static friction section and then drops down to the force of kinetic friction. Okay. So there are two different kinds, right? So right here, we get the static friction, and then the force of kinetic friction is here. So once you break the static friction, the force that friction applies is going to be less. We can think about this conceptually because the force of friction is really a bonding of the floor or of two surfaces together. It's a really light bonding, right? If there was no bonding, if there was no electromagnetic force there, then we would not be stuck together. So this is why you get stronger bonding, right, with something that's glue, right? You're having a really light bond, so there's going to be a lot of friction there. Now, something I want you to notice as well is that our box has static friction all along this area, right? I can push on the box anywhere from 0 to the limit, and I will not have an acceleration. Since friction is a responds to another force, is if it's still static, that means that the force is equal and opposite. Remember, this is not Newton's third law. So let's say I am pushing with this amount of force here, right? So I can redraw my box, and I have some force here, and I have my friction force, right? These two forces are equal. Now, sometime later, I get a larger force, but my box is still stationary. So I'll draw that to the right over here. I have increased my push. I'm trying to push it harder. but it is still equal. And so there's still no acceleration. It is only once I break the force of static friction that then I jump down to my kinetic friction. Okay, so force of friction is calculated by a pretty simple equation. Force of friction is equal to mu, multiplied by the force normal. Okay. Remember, a normal force is the force that a surface applies to an object perpendicular to that surface. Now, we will have two different mu's, right? We'll have a mu for static friction and a mu for kinetic friction. Okay, so there'll be two different coefficients here. So let's consider a situation in which static friction is not at the maximum, right? We mentioned that it could be anywhere between 0 and its maximum, and that is relative to how much the pushing force is applied. So I've put in a couple of numbers here. So we have a force of gravity of negative 100, right? We're going down. And then the force normal is going to counteract that at the same amount since it is not accelerating up or down. And then the mu for static friction is going to be 0.5, which means that the force of static friction is 50 newtons at its maximum. It can't be any bigger than that. It can be smaller, but it can't be any bigger. So if I have a force of push that is 25 newtons, right? I have not exceeded the maximum force of the push, which means that they are going to be equal to one another, right? My box is still stationary. Static friction is holding. So one error that we might make is to consider that, well, since the mu of static friction gives us a 50 Newton maximum for the force, well, then that means that the force of static friction is always going to be 50. Now we can add up our numbers and we'll see that the force of friction would then be accelerating our box in the leftward direction. This is a problem, right? Our box is stationary, which means that the forces all have to be in equilibrium, which means that at this time, actually, it is not 50, it is force of friction is equal to 25 newtons, just in the opposite direction. We'll call that the negative direction. Okay. So that way, all of our forces actually add up to 0. So you need to be careful when you're considering static friction because that force is variable based on the applied force. Now, if we were in motion, things are going to be a little bit different. So now I have a coefficient for kinetic friction that is smaller, right? The kinetic friction coefficient is going to give us a smaller force, so the coefficient also needs to be smaller. Now let's change around our force of push here, and let's increase it over that 50 Newton mark. Let's turn it into 75 Newtons, okay? So now we can consider the situation for a box that is in motion and is also now going to be accelerating. So what we can do at this point is we can solve for our force of kinetic friction. So we're going to multiply our normal force by the kinetic friction coefficient, 0.3, which is going to give us a force of friction of 30 newtons. And if we wanted to find our acceleration, we would need to get the net force on our box. And we can do that by adding up the different forces in the different directions. The vertical direction, right, has equal and opposite forces, so they cancel the 0. But our net force here is going to come out to 45 newtons in the horizontal direction. Now, let's take a moment to consider a couple of different situations. The first one I want us to consider is a box on top of a cart. Now, we're not going to be concerned about all of the different forces acting on our cart, but we are only going to be concerned about the forces on the block. So, the first thing that we're going to do, since the cart uh, has a level surface, then the force normal and the force of gravity are going to cancel out in this case. Now, at some point, the cart is going to begin to accelerate in the rightward direction. Now, according to Newton's first law, the law of inertia, right, our box is going to resist that change in motion. So something is going to have to accelerate that block so that it stays with the cart. So think with me for a moment. What would be the force that causes it to accelerate? So first off, we know that if the cart is moving to the right, accelerates to the right, then something else is going to have to accelerate our block to the right. So I know I'm going to have some force that pushes it in this direction, right? So some force causes it to accelerate to the right. But what is that force? Nothing else is really in contact with my block. And we know that in the horizontal direction for projectiles, there's nothing to accelerate it in the horizontal direction. So the only thing that could be accelerating the block here is the force of friction between the block and the cart. Now, this seems a little bit strange, right? Normally, there is some sort of applied force to our box, and that is what's going to happen. The thing is we often have learned about the force of friction being resisting motion. This actually is incorrect. What it does, friction opposes slipping on surfaces. So that is a major difference. So if we think about our example at the top of the page, our box is going to resist slipping off of the cart. Now, this directly counteracts the law of inertia, which is saying that we are going to stay at rest. So we have the law of inertia saying that we want to keep our lack of motion, and then friction is going to cause us to not want to slip off of where we are. So friction is the thing that's going to keep our box on top of the cart here. Okay, so we have one more example that we need to think about, and that is that the force normal is not always equal to the force of the weight or the force of gravity. So what we're going to be doing is we're going to be considering a wall, and we have a book that is being pressed up on the wall by my hand. I'm not going to try to draw a hand because I stink at it, so I'm just going to draw maybe a stick figure, and it's got some fingers pressing up against it, right? Yep, looks horrible, right? Well, that's a hand. Don't worry about it. Cool. So here we are going to have the force of my pushing into the wall. And since the box is not, or my book is not accelerating in or out of the wall, I'm going to have a force normal coming off of the book that has the exact same amount of force. Okay. So here are my two forces for the force normal. So the force of normal is caused by the wall, which was caused by the force of my push. Now, the book also has a force of weight pulling straight down like before. Okay. Now, if we wanted to figure out if our book started to slip down the wall, we would need to figure out that force of friction. So let's say for now that the force of the weight does not break the force of friction. And so these two will be in equilibrium. So notice that in this case, the thing that causes the force of friction is the force of gravity pulling my book down. And the force normal in this case doesn't have anything to do with um, the, the force of gravity. So be careful as you consider this. It is always what is going to cause the slippage, the thing that you want to worry about. So in this case, the thing that would cause our box or book to slip down the wall would be the force of gravity, and the force of friction is going to oppose that slippage. Notice, though, that the force of friction is pointing up, which seems a little bit strange, right? We've been dealing with force of friction so far only in the horizontal direction, and now it's going directly upward, which for some reason seems a little bit strange. So, what I want you to do is I want you to consider, and I'm not going to draw more hands because you'll make fun of me. I want you to consider putting your two hands together. I want you to do this right now, palm to palm. And I want you to imagine one hand to be one of the two objects, right? We have two objects here. We have the wall and we have our book. That's the surface interaction that we're concerned with. Okay. So imagine one hand to be the book and one hand to be the wall. And then concentrate on each hand in turn. Move one hand lateral to the other, right? One up, one down. Okay. Slide one hand over the other in the direction which the objects would tend to slide. So if you have your left hand being the book, that's going to be sliding downward. That left hand should be sliding downward. And then feel the force that's exerted on that hand and put that force on the corresponding object in your force diagrams. So, as you think about force of friction, you can use this little thought experiment, this little demonstration just with your hands to help you understand where the force of friction is going to be.